This is the second installment in the series of lectures on the MANOVA. This one is called Behind the Scenes, and I'm Jennifer Ripley. Welcome back to our big old MANOVA competition cake that we are building here. In this one, I'm going to be covering the behind the scenes. What that means is, what are all of the components? What are all of the pieces of the puzzle? I'm not going to have you calculate in MANOVA. It takes all day, for one, and it's probably not the best use of your time when a calculator or a computer, and particularly, does it so much better than we do. But I do want you to understand what the computer is doing behind the scenes. Essentially, this is what's going on inside my computer whenever I tell it to run a MANOVA, so that you understand conceptually what's happening in this statistic. So there's some new words to learn here. You're making inferences. Now, you've been making inferences in ANOVA as well, meaning that you are trying to test a hypothesis and come up with some conclusions. It's an inferential statistic. But this time you're making it about vectors, they're called, all right? Vectors of means. In the past, when you did an ANOVA, that would be making an inference about the mean. Particularly, it's looking at the mean, the variance, and then the number of participants, and telling you what's going on there within a certain degree of freedom. So that's the ANOVA, but when you get to MANOVA, you have to use vectors. The reason for that is you have more than one dependent variable. And when you have more than one dependent variable, you can't just put a mean score. You now have two mean scores. If you have two dependent variables, 3 mean scores and 3 variances and 3 degrees of freedom, if you have 3 dependent variables. So you now can't do that anymore. So a vector is a simple thing. It is just a row or a column. Doesn't really matter whether it's presented as a row or a column, but it's a set of data presented either as a row or a column. And the analysis that's being done behind the scenes is looking at the sums of squares. So that should sound familiar to you from ANOVA, the sums of squares. You understand that. You squared things and summed them. But you're also looking at something new. This is the sums of squares of cross-product matrix. All right? So it's creating a matrix. It is a little bit like stepping into a movie, like the Matrix movie. And the realities are a little different because we're in the mathematical world. Right? But in an ANOVA, you're looking at the sums of square matrix. And in a MANOVA, you have the sums of squares and cross products, both. So I don't want you to be embarrassed one day if you talk about it and you're not kind of understanding fully that really what we're looking at is this SSCP. So I want to introduce that concept to you, and hopefully you'll understand it by the time we get done with this brief lecture. And when you see a picture, this is a picture of a vector. Some people find it helpful. Here, because we no longer just have a mean score like you might have in a 2D, right? If we had a 2D, you might just have Z and Y there, and you would plot the person on the Z and the Y. But now we have more than that going on. All right, we have at least 3 variables in a MANOVA, sometimes more. So we essentially have a point out in space, in 3D space. And so we have to develop all kinds of exciting mathematics to be able to handle that. And it gets beyond the ability to even draw a picture of it whenever you get to 4 and 5 and 6 kind of dimensions being looked at. But this is just a picture of a vector. If this doesn't, make it all clear to you, then don't worry about it. Some people find it helpful. Some people just stay in the mathematics or the conceptual ideas, and that's fine. You don't have to understand the picture. All right. So if you remember, when you ran ANOVAs, to get a significant ANOVA, what you would have was a significantly different mean score for each group. So that's your levels of your IV on their scores on the DV. And if you had something significant, then within each group, you would have low variance, right? So just for Black females, if you're looking at just that group and comparing it to other groups, Black females would have low variance, meaning there's not a lot of spread. They're all kind of clumped together in their scores. But then when you compared that group to another group, there would be a lot of difference. There would be between Black females and white females, you would have high variance. And that just means a high difference, different scores there. So if you had low within group variance, but high between group variance, you would get a significant ANOVA, and that's how it would be done. You got this by calculating the sums of squares of deviations from the mean of the dependent variable. right? So if you had to hand calculate this at some point in your life, you would have to do how far was each score from the mean of the dependent variable and sum and square it. To do it. And you would look at the differences between all the black females in your study, for instance, all white females, all black males, and all white males. If you were looking at Caucasian and African American as your two categories of race that you're going to investigate in this particular study, and male and female as the two categories you're comparing in this study. So you have two independent variables, each with two levels, which leads to a 2 by 2 or 4 categories that you're comparing. So within group sums of squares would be the variance within each of those groups. So we would hope black females would score similarly if we want a result. We want a difference, if the goal is a difference. In the end result, significant difference. We would want all white females to be scoring similarly, all clumped together, low variance. All black males, low variance. All white males, low variance. We would be looking at the degrees of freedom, both between each of those groups and then within the group itself. Right? And those bits of information, all right, are what is going in the cake. The degrees of freedom, the sums of squares, within groups and between groups are going into the cake, and this creates for us an F, right? A value we call F, which indicates how different the groups are in that ANOVA. And at some point, the value of F is large enough that we say that difference score is not due to chance and a probability of p.05 or less. And we say that the groups are significantly different from each other. So that's how it happened once upon a time in easier land of ANOVA. Hopefully you have some understanding of that. If you don't, you might want to go back and review that material so that when we go forward to this next thing, when it gets more complex, you have a solid grounding. So remember now, we're going forward, we're making inferences not about means and sums of squares, but about vectors and sums of squares across products matrices. So what is that? A matrix is just a table of numbers with a certain amount of rows and a certain amount of columns. Right? So a matrix would be both rows and columns of data. That matrix, right, so that row and column, that grid of data, has the sums of squares for all the dependent variables and all of their what's called cross products or covariances. There's a video in here about covariance. I'm not going to go into great detail about what covariance is, but it's essentially how two continuous variables vary together or differently, meaning their spread is how similar is their spread, how different is their spread as they move back and forth across their number lines, how much do they vary similarly or different. It's kind of a really basic understanding of covariance. So what happens is that you can't just do this with regular algebra. You have to use matrix algebra to allow the computer to create a single number to tell us if the amount of variance for this matrix, right, of data with rows and columns and more than one dependent variable, if it's different. This single number is called a determinant, all right? So once in a while, you'll see someone that they might give you the determinant score for their MANOVA, and you would know what that is. You would know that that's actually some composite score of the entire matrix. And then what it does is it says, okay, I want the determinant within groups for all of that, the matrix for that, and I'm going to look at the determinant between the groups, all right? So again, we're still comparing between groups and within groups, just like we did with ANOVA. When we compare those, we can get a number, and that number will tell us whether between group and within group is significantly different from each other. All right. This is a little bit of behind the scenes of how it gets broken down with variance and covariance. So this is how those sums of squares and then sums of cross products and deviations happen. The first top one you see there is omega squared. It's a common indicator of variance, meaning it's the most common way, particularly in psychological statistics, that people will calculate variance. If you look at it and you break it down, what I circled there, M stands for the mean, X stands for each individual person's score on the dependent variable. So you looked at the difference between the individual score and the mean score, so looked at the difference, you squared that, you summed them all up, and then you got yourself, you put it over the N, and you got yourself a variance score. So if you took an undergraduate statistics class, you probably had to do this at some point, and maybe you've blocked it out by now, but maybe it's still in your recesses of your memory. And you can go do this if you want to, but if you can just trust me that basically the components you're looking at are a sum, a different score. It's been squared to be able to standardize it more, and we put it over the N so that the number of participants influences the strength of the variance, or so that really helps. So in covariance here, right, when you get to the covariance, this one is the sums of cross products of deviations about the mean. So look there, you got 2, right? Because you got, say, 2 dependent variables. We'll call one X and one Y. And we're looking at the difference between the X and its mean. Okay, so each individual person's X score and the mean, and then each individual person's Y score and the mean. We're going to multiply those because we've already multiplied them. We're not going to square it because it's already kind of maximized. It's already a big number. We're going to sum all those up, though, and we're going to put it over N, and that will give us our covariance, or the sum of cross products of deviations about the mean. This is a great way to be able to look at things. And what's happening is behind the scenes, your computer is calculating these scores, the variance and the covariance, to put into a larger matrix of data. Okay. Now, this would be a matrix of data if we had 4 dependent variables here. So I have omegas here because what's going to happen is you're going to have the regular old omega here, and then you're going to have the covariance of these 2, the covariance of these 2, and you can see X and Z together, and then the covariance of X and Q with each other. And then you have Y squared, Z squared. So each of them on their own, and then each of them with each other, and that gets us our variance and covariances. Some people find this helpful, just to call it this. The ones along the diagonal are actually the same thing as the sums of squares that you would see in any ANOVA, because it's really just looking at the variance within each on its own. So X all on its own. Remember, this is 4 dependent variables, Y on its own, Z on its own, Q on its own. But then you have to look at the cross products, right? And so you get these cross products of each of them with each other. By the time you do all that, you got a whole lot of numbers, and you got yourself a matrix. Right? And that's what the sums of squares of cross products matrices is doing in the background. Right? So it's not just looking at the mean score. It's not just looking at the variance. Right? It's developing a determinant out of this matrix of data. First, it's going to do it between groups, and then it's going to do it within groups, and it's going to compare them to each other, and then you'll be able to find out if you have a significant difference with those 4 dependent variables altogether. So if you had a study with only 2 dependent variables, it's more simple. You would just have like the X and the Y portion of it. Sums of square X, sums of square Y, and the cross products of the 2. It's a more simple analysis. But MANOVA can handle quite a few dependent variables and do just fine. All right, there's this video here on YouTube, and I will leave a link for you for it. But it is a great little video that will show you about covariance matrices.
Hello, and welcome to the next video in my series on basic statistics.
Okay, I'm not going to play the whole thing. I just wanted to play the beginning for you so you could find it. If for some reason things get unlinked from each other in the future. It's about a 20-minute video, but it goes nicely through the concept of covariance if you'd like to go in more depth. Okay. All right, we're at the end of the behind the scenes. Those are some basic concepts that I want you to understand, and being able to understand the determinant that's being looked at, that it is between groups and within groups, just like it was with ANOVA, but this time it is a matrix of data that you're looking at, not just a column of data, one column of data. So hang on tight. That was video number 2 of the 5-part series on MANOVA, and I'll be going into the next video. We'll be talking about main effects and interactions with our independent variables.